I look at it, I just see a sheet with a bunch of horizontal lines, and it looks fine to me, but I don't know.
Horizontal, yeah.
Yeah, let's see, that's all. Okay, great. Implicit differentiation. What we're learning today is, in my opinion, easy, okay, but also really important, because so often you're going to be applying implicit differentiation, and its origins are from the chain rule. You'll be using implicit differentiation to get the first derivative, and implicit differentiation to get the second derivative. Well, hey, let's start. Implicit differentiation. And it's primarily, it's used for many, many purposes, but it's primarily for non-functions. Let's say I had a relation, and it's not a function. Suppose I had a relation such that if I graphed it, the graph ended up looking something like this. Okay, let's say the graph was a non-function, and it looks something like that. Okay, and someone said, okay, right here at x, I would like to get the slope of the tangent at x. Well, what's the problem with me getting the slope of the tangent at this value x?
There's a nose and hair in the way.
Yeah, there's a nose, there's hair, maybe the chin. There are many different places where I have tangent lines, right? And so I can't just say, you know who that is, by the way?
Donald Trump.
So you understand that in a situation like this, we need an expression for the first derivative that involves x's and y's, because I have to make a distinction between that point, that point, that point, that point. And so thus we have implicit differentiation. And that's why we have it. So I can get first derivative there. Okay, let me get my notes just a second. By the way, here I'm going to skip all that. Okay, I'm going to skip that. Okay, there's a reason why it's called implicit differentiation, and it's because there's two ways to define a relation that you would graph. One way would be explicitly. And when you define a relation explicitly, that means that you get y on one side and you get all your x's on the other side, you know? And it doesn't matter what's happening to the x's, but you need a single y on one side, all your x's on the other, then your function or whatever is defined explicitly, okay? But if I've got a relation that's defined implicitly, then you have all your x's and y's mixed up. You have them with each other. So some examples of implicit form would be, whoops, even something as simple as this, where I haven't solved for y. And if I did solve for y, I would end up with a plus or minus on one side, which means my one equation would turn into two separate and distinct equations. So it's better just to define the quantities implicitly. Or another example of an implicit definition would be one just where they're all mixed up together randomly. And again, you couldn't solve for y no matter how hard you try, right? You can't solve for y, and frankly, I don't even want to try. Oh, I don't want that. The y's cancel here. They call this like a 4. Okay, but you see what I mean? You can't solve for y. It's not possible. So the relation is defined implicitly. And so we need to be able to take derivatives of relations that are defined implicitly, and the way we're going to do it is by using implicit differentiation. So let's go ahead and do an example. Alrighty. Get dy dx for x squared plus y squared equals 9. Let's go ahead and do something incredibly simple, then we'll get harder and harder. Okay. In order to get the derivative, I'm going to take the derivative of both sides of this equation. That is, I'm going to do this. I'm going to say, okay, let's get the derivative of the right side with respect to x, and let's get the derivative of the left side rather with respect to x, and the derivative of the right side with respect to x. And you'll notice I'm getting the derivative with respect to x because that's what they're asking for, dy dx. They want the derivative with respect to x. So let's go for it. What's the derivative of x squared with respect to x? 2x, that's easy. But what's the derivative of y squared with respect to x? Yeah, you're right. How many people know it's 2y dy dx? So how many people learned this last year? Oh, you guys are all so smart. And you remember too, that's amazing. Yeah, exactly. We're treating y squared as if it's a chain rule situation. We're saying it's the derivative of whatever squared, right? And the derivative of whatever squared is going to be 2 times whatever times the derivative of whatever, right? What times the derivative of whatever that thing happens to be. And that's what we're doing here. We're treating the y as if it's a whatever, you know? So yeah, the derivative of y squared is 2y dy dx, right? Chain rule. Y squared is, you know, that. And then the derivative of 9 is equal to 0. And then, of course, what happens next is you solve for dy dx. Subtract 2x from both sides, divide both sides by 2y, and I get dy dx equaling negative x over y. And you'll notice, just as I was talking about here with Donald Trump, we need to have an expression of dy dx that have x's and y's in them, right? So that when I graph that circle, when I graph x squared, here's negative 3, here's 3, here's 3, here's negative 3. When I graph x squared plus y squared equals 9, and someone says, hey, get me the slope of the tangent at, let's say, get me the slope of the tangent at, what's this point here going to be? That the 45-degree point. Just a second. That's going to be 3, so that's going to be 3 over rad 2, which is 3 rad 2 over 2. Okay, so this point here is 3 rad 2 over 2, comma 3 rad 2 over 2, right? And this point here is 3 rad 2 over 2, comma negative 3 rad 2 over 2. All right. Well, if someone says, get me the slope of the tangent at x equals 3 rad 2 over 2, you can't give them one answer, right? There's 2 choices depending on where on the circle you are. So if someone says they want the slope of the tangent, they're going to have to tell you the x and the y, okay? So for example, if we wanted dy dx evaluated at 3 rad 2 over 2, comma 3 rad 2 over 2, that is, I want the slope of the tangent right there, then I can go ahead and plug in. I got negative 3 rad 2 over 2 over 3 rad 2 over 2, which gets me negative 1. And you observe that matches your graph. At 3 rad 2 over 2, comma 3 rad 2 over 2, sure enough, the slope of the tangent appears to be negative 1. And similarly, the slope of the tangent here, if I were to put 3 rad 2 over 2, comma negative 3 rad 2 over 2, I would get a slope of positive 1, just as my graph shows. I hope by now, believe it or not, this was almost all introduction. I hope now you're appreciating why when functions, or not functions, when relations are defined implicitly, you know, you can't just solve for y. You're going to have to figure out a different way to get the first derivative, and that different way is to do implicit differentiation, so that you can get the slope of the tangent wherever they want you to. Any questions or issues so far before I start giving you increasingly harder examples? All right, then, hey, let's do a harder example.
The hardest one.
I'll give you the worst example. Imagine it. Okay. I'm going to skip that. That's too easy. And I'm going to go to that. Example number 2. X, y squared equals 6 at 6, comma 1. Get y prime. Okay. So you got the equation xy squared equals 6. Get the slope of the tangent at the point 6, comma 1. Would someone like to tell us all in words? While everyone else is doing it. Tell me in words, how are you going to get the slope of the tangent? Yes?
Product rule.
Thank you. You're going to have to do product rule. So please do product rule now. I'll give you, 60 seconds.
Mr. Trina,
Yes?
I go to Russian.
Sure. I can answer that question too. The answer is yes. Parth, question?
Oh no.
You good? I'm going to do the first step. You guys keep working. But I'm going to show the first step on the board. You should have gotten this as your first step. Okay. Well then, hey, I'm going to go for it. Got to solve for dy dx. So I subtract y squared from both sides. Then I divide both sides by 2xy. And then at this point, I would go ahead and cancel the y's. Although you got to keep in your mind now that actually your slope is undefined at y equals 0. But I'm going to cancel the y's. So I get negative y over 2x. And that's going to be evaluated at 6, 1. So dy dx at 6, 1 is going to be, what is that, negative 1/12? How many, is negative 1/12 correct? Or is it not correct? It's correct?
Yeah.
Okay.
I was worried it wasn't.
What's that?
I was worried it wasn't.
All right. I was too. Any questions or problems on that? Yes?
Instead of finding first dy of dx to be equal to negative y over 2x, can you just put the from the higher end for the x and the y's?
Oh, yeah, sure. Lauren says, hey, Mr. Shana, you're such an algebra teacher. Why should I solve for dy dx? Can't I just plug the numbers in right now and then solve for dy dx? And the answer is yes, absolutely. In fact, that's probably better than what I do. I just do it my way because I'm such an algebra teacher. I don't know. I like to solve for things before I plug in, but actually plugging in is better. Okay, so here comes the next one. You guys ready? I'm going to give you one where you don't get to plug in. Now I have to foil Lauren's shortcut here. So here, you guys, give this a try. Y to the third plus x squared y squared equals 7 minus 5y. Find dy dx. Now, you know you're going to have to take a lot of implicit derivatives here, and so you're going to be sprouting a lot of dy dx's. You're going to get a dy dx here, you're going to get one of the terms of this product rule will yield a dy dx, and you're going to get a dy dx there. I've got 3 dy dx's. Someone tell me, what am I going to do with them?
Get them on the same side. You're gonna
Thank you, Daniel. Get them all on the same side. When you sprout a bunch of dy dx's, get all your dy dx terms on one side, get everything else on the other side, and then solve for dy dx. You're going to have to factor. So good luck. Or should I just show you this and then give you another? I mean, let's do that. Here, I'm going to show you this and then give you another one of equal hardness. Okay, so step one is you're going to have to take the derivative of both sides of the equation. So I'm going to take the derivative with respect to x of the left side and the derivative with respect to x of the right side. That's step one. Let's go ahead and do it. Are you okay that the derivative of y to the third is 3y squared, but then I have to sprout the dy dx because of the chain rule? And then I'm going to do product rule on this guy. The derivative of the first is 2x. I don't have to sprout a dx dx. I mean, I could if I wanted to, but what would dx dx be equal to? 1. So, I mean, it doesn't really help or hurt. But, so I got 2x times y squared. Good. Plus x squared times 2y times dy dx. Alrighty. Equals, the derivative of 7 is 0, yay. The derivative of negative 5y is going to be negative 5 times 1, but then I have to multiply by the derivative of y. You know, this is like y to the first. So the derivative of y to the first is 1y to the 0, which is just 1, but then I have to multiply by the derivative of the y, which is dy dx. Any question or problem on that? Does that look up? You look quizzical. Maybe your face just naturally is quizzical. I think so. Okay, that's fine. Some people, you ever see some people where their faces are just naturally mean, but then when they smile, their face totally changes? You know, that's what I'm afraid is happening to my face. My face is like, when I'm relaxed, you know, I'm just naturally mean faced. But then when I smile, I like to change it a little. So anyway, let's get all my dy dx's on the left side. 3 squared times dy dx. Plus 2x squared y dy dx plus 5 dy dx equals that guy. The only term that doesn't have a dy dx in it. And what? Oh, the minus? Did I forget a minus? Yeah, I gotta tell you, you're gonna have to be really careful with your algebra on these types of problems. And then I'm gonna factor the dy dx out. So I got dy dx 3y squared plus 2x squared y plus 5 equals negative 2xy squared. And then finally, I solve for dy dx. dy dx equals negative 2xy squared over 3y squared plus 2x squared y plus 5. Ta-da! There it is. There's your expression of y prime. Okay.
Beautiful equation.
You guys ready to do one on your own? All right,
Yes.
here it comes. And I'm not going to have you plug in any numbers, so you'll have to do the algebra. You can't do the Lauren cheat. Here we go. I like this one. X squared y squared equals 2y to the third, get y prime. Good luck. By the way, is there anyone here who's putting y primes instead of the dy dx's? Anyone doing that? Because if you are, that's fine. Just if you're going to put y primes instead of dy dx, man, you got to be super careful that you make it incredibly obvious that it's y prime and not y, or you're going to get a totally wrong answer. So me as a teacher, I prefer dy dx's when I'm showing students so that there's just absolutely no ambiguity, you know? But you can use y primes if you want. It's less writing. It's just risky. Okay, good luck. Take the derivative of both sides of that equation. Derivative of the first times the second plus the first times the derivative of the second equals this guy. Please look, hopefully your first step was that.
Oh, I did not see the 2y. Wow.
Derivative of y squared is 2y dy
Oh, that's
dx.
right. That's right.
Any question or problem on that first step? Alrighty. Well then, hey, let's get all our dy dx's on the left and all our other stuff on the right. So I got x squared, let's call it 2x squared y dy dx minus 6y squared dy dx equals negative 2xy squared. And now I'm going to factor the dy dx's out. Dy dx times 2x squared y minus 6y squared equals negative 2xy squared. And then I'll divide. I got negative 2xy squared over 2x squared y minus 6y squared, and ta-da. But interestingly enough, if, oh, let me wait. Any question or problem on that? How many people got that? Okay, yay. And Lauren, question?
Would you want to simplify too?
No, dear God, no. Oh yeah, I guess you can cancel the y's. Yeah, cancel the y's. Yeah, sure. Yeah, well, let's cancel the y's. Negative, oh, and the 2. Yeah. Okay, yeah, you guys are good simplifiers. Glad to see that. So I got negative xy over x squared minus 3y. So is that what, how many people got that answer? Oh, Miss Lofgren would just love you guys. Okay, and but I want to remind you, the Lauren method is beautiful, you know? I mean, if they said not get y prime, but if they said get y prime of, what is it, 1 comma, wait, no, 1, 2? No, rad 2, oh, that won't work. Oh, poo. I think I have it on my paper. Just a second. I gotta look at my notes. I can't do it in my head that quickly. 2 comma 2. Okay. I just want to remind you, the Lauren method is beautiful. If they want y prime at 2 comma 2, then once I got it here, you know, once I got it here, I would plug in the numbers. Why not? Why? Yes.
Oh, sorry.
Okay. Yeah. I mean, let's just plug in the numbers. So now, you know, my x is 2 and my y is 2. So this guy becomes 2 times 2 times 4, which is 16. So I got 16. And this is 4 times 2 is 8 times 2 is 16. So I got 16, you know, y prime equals 424 y prime. So I got 16 equals 8y prime, so I got 2 equals y prime. I think that's pretty darn easy. And I think that many of you may find it easier than doing all of this algebra. So I just want to say again, if they do implicit differentiation, but they want it at a point, take the derivative and then immediately plug in your numbers, and I think it'll work out just swell, you know. Okay, was there anything? Yeah, Andrew.
It's okay if we have, so all the sides are flipped.
Yeah, that's fine.
Oh, okay.
Yeah, you
So-
multiply top and bottom by -1. Multiply numerator and denominator by -1, and you get xy over 3y minus x squared. That's
I like the
beautiful.
least amount of negatives.
Yeah, me too. You know, because you're a positive person.
Yeah.
Yeah, me too. Okay, great. Well, guess what happens next? We just spent the last 20 minutes finding the first derivative. What's going to happen now? Yes, ma'am. The second derivative. And you know what the second derivative is for this type of problem? Twice the fun. Here it comes. Example number, what the heck are we on, 3 or 4 or something? Example 5. For x squared plus y squared equals 25, find y double prime. Okay, find y double prime. Well, as you know, to find the second derivative, step 1 is to find the first derivative. So let's go ahead and do that. I'm going to take the implicit derivative of both sides. So I get 2x plus 2y times dy dx equals 0. So I get dy dx equals x over y, negative x over y. You guys okay with that?
Yes.
So what would you have me do now?
Take the derivative again.
Thank you very much, Andrew. Like anything you really enjoy doing, you do it again and again. And that's what we're going to do here. Let's take the derivative of this guy. Okay? So on the left side, I got the derivative of dy dx, which gets us that freaky way of writing this second derivative, d squared y over dx squared, a way that has no actual meaning other than it's a symbol for the second derivative. And then this side here, I'm going to take the derivative, and what special rule starting with q am I going to have to use? Yeah, quotient rule. So I got the derivative of the top times the bottom minus the top times the derivative of the bottom. But the derivative of the bottom is y prime, correct? The derivative
Yes.
of y is not 1, it's y prime.
Yeah.
Okay? All over the bottom square. Well, now, what would you have me do? Because I want just x's and y's here. I don't want this y prime on the right side of this equation. So what should I do? Because I don't want that y prime. I hate y prime. Gosh, I wish there was an expression for y. Yes, Omar?
Why don't you make it dy over dx?
Yeah. Oh, you want me to turn this into dy over dx? Okay. But I still don't want dy over dx. I want the right side of this equation to be nothing but x's and y's.
Move it over.
What's that?
Just move it over. Yeah.
No, don't do that. Yes, Abigail.
Plug in the first derivative.
You mean plug in this guy for dy dx? Yeah, absolutely. And that's the only thing I'm teaching you here. I'm just teaching you that when you take the second derivative and you sprout a dy dx, you're going to want to substitute your value for dy dx into the equation. So I got negative y plus x times dy dx, which is negative x over y squared. You see that? Now it's good. I'm gonna simplify this. Something I was showing my son yesterday. He's in calculus AB. That's what they offer at Claremont. They offer a year of AB and a year of BC. He's in calculus AB, and I had to remind him last night how to deal with complex fractions. So I'm going to remind you guys as well. When you have a complex fraction, like having a y in the denominator of a part of a numerator, you have to multiply top and bottom of the fraction by whatever that denominator is. So do you see, I have to distribute this y, so I get negative y squared minus x squared, because the y's cancel. And here I get y to the third. And then here's the last thing. But before I go on, any question or problem on this? I took the implicit derivative, and just like I did before, and solved for dy dx. Then I took this second derivative, I took the derivative again, and I found that I had sprouted some dy dx's on the right side. Wherever I sprouted dy dx on the right side, I'm going to have to substitute this expression for dy dx. And then I had to simplify this. And here's the last thing. You look in the back of the book. And the back of the book says that this is not the answer. The back of the book says the answer is this. Someone tell me, why is the answer negative 25 over y to the third? Yes, Andrew?
Because x squared plus y squared equals 25.
Oh, so be aware of that. Your answer may not agree with the book because they'll make some cool substitution at the very end. And yeah, instead of having negative x squared minus y squared, they'll just say, hey, x squared plus y squared is 25, so negative x squared minus y squared is negative 25. Let's just put a negative 25 in there and it'll be really cool.
That's crazy.
Okay. So you guys okay with that?
Yep.
You want to do one on your own?
Sure.
Sure? Oh, I like that, sure. Hey, you got 2 minutes to do this. It's kind of going to be a repeat of that because I can't make them too difficult because they just end up taking a lot of your life. I don't want to do that. Hey, let me see how far you can get on this. Y squared minus x squared equals 4. Get y double prime. Good luck. If you get 4 over y to the third, you win. Alrighty, well, hey, just as closure, I know some of you are doing this, but I'm sorry, there's not enough time. So as closure, when you take an implicit derivative, okay, when is the only time you're going to be sprouting y primes or dy dx's? When you take the derivative of what? Yeah, when you take derivatives of y terms, you're always going to be sprouting those y primes or dy dx's. And to get the first derivative, remember, get all your dy dx's on one side and everything else on the other. Solve for dy dx.